right, so I'm going to talk about KeeperIO, which is, if you were in some of the sessions yesterday, it got mentioned a couple of times. I should, at the risk of throwing Chandra under the bus, but I will. So Chandra chairs the TCG storage work group, which is where a lot of the heavy lifting of KeeperIO has basically been done. And we've moved from sort of talking about what is KeeperIO in gory detail to trying to talk a little more about how one would go about using it. So I'm going to do a little bit of what is KeeperIO and a little bit of how one might use it. And part of that is trying to sort of foster interest in using this technology. Okay, so a little bit about the intro. So if you're familiar with self-encrypting drives, which have been around for quite some time, and again, TCG with Opal specs have been around for years, enterprise SSCs as well. You basically have encryption that's inside the drive, and effectively the key management is handled all internally to the drive. So the actual media encryption keys are all internal, they never come out. The connection between a host, if you will, and the drive is typically something on the order of an authentication pin, which you may have set up as part of your personalization. And there is a relationship typically in implementations between that authentication mechanism and how one goes about unwrapping keys internal to the drive, but that's essentially the connection. There's none of the keys ever come out of the drive or are accessible, right? So in some customer environments and user communities, there's a lot of concern about, were the keys generated correctly, is there enough entropy, all kinds of issues, and I've seen almost religious debates about whether self-encrypting drives, which are managing the keys, is going to be acceptable or not. And a lot of financial institutions are sort of split on acceptability. So this technology is different in that we are taking advantage of the encryption. The encryption engine is on the drive. However, the key management is actually, for the most part, external to the drive. In fact, the drive, when it first comes up, if it's a KeeperIO drive, it's unlikely to have any keys in it at all. So you've got to basically provision the keys before it can actually start doing anything. There are multiple specifications involved with KeeperIO. The NVMe TP4055 is the document that sort of sets the connection or basically describes KeeperIO. A particular implementation of KeeperIO is what the Trusted Computing Group has done. In theory, you could actually have your own version of KeeperIO if you wanted to do that. And of course, you would have to go and specify all the components that the TCG has already basically done. On the Trusted Computing Group side, probably the core document is the SSC. This is where all of the details are provided in using KeeperIO. The sys document is essentially the how to map the sort of generic KeeperIO SSC into NVMe, for example. So what's sort of the connection points there? There's an application note that is very close to publication. I don't know that it's been published today, but I think we're like on the cusp. There's a public review version out available. So this document is something you can actually see, but the final version of that is very, very close. And then the last piece that we're working on right now is the test cases, which one way to think of this is the document that will sort of help you determine whether a drive is basically Keeper IO compliant, or at least the TCG version of Keeper IO compliant. There is one aspect of Keeper IO that's kind of interesting. Rather than redefining how to go about doing things like key injection and whatnot, the TCG specifications actually leverage some of the OASIS key management operability protocol to deal with that. And one of a bit of the backstory on that is, in theory, it may be possible where a key management server may be able to pass keys down through a host and ultimately proxy those to a drive, but it may not actually see the keys in transit, in theory. So, and using KMIP is one of the enablers for that kind of functionality. That's yet to be seen, but it was something that was talked about and discussed. Now, again, if you're familiar with self-encrypting drives, the number of media encryption keys that a drive typically has is maybe 1, but no more than 1024, because you've got these bands. There is no such limit with Keeper IO. The limit is how much the host is willing to take on in terms of managing keys. So if you want to have a different key for every file, go to it. But you will need, on the host side, the ability to sort of manage that. So there's no restrictions on, from a Keeper IO perspective, on the number of keys that can be used. There are going to be some restrictions on how many you can use at any given point in time, and we'll get a little into that. Okay, so I've already probably talked to a few of these points now. Conceptually, what's going on from a Keeper IO perspective is you've got a drive, you've enabled this functionality. There's a key cache that exists on the drive, and there's a need for some key encrypting keys, wrapping keys, so that you can pass keys down securely. So part of the process is, in sort of getting the drive connected up to the host and functional, is establishing these key encrypting keys. If you've only got a single namespace from an NVMe perspective, then you're essentially going to have a wrapping key. Those are used to protect the keys that come down to the drive. If you have multiple namespaces, you'll have a wrapping key, a key encrypting key per namespace. Then you're moving keys into this key cache prior to using them. And think of this key cache as a volatile cache. In other words, if you power cycle the drive, all the keys go away. They're also, let's say that the key cache is 1,000 keys, and we'll say you've got one namespace. But if your host is using 10,000 keys, it's going to have to figure out at any given point in time which 1,000 keys that it needs to have loaded in the drive prior to actually needing to use those. So that's a bit of the dance that needs to go on. But in general, this is perceived to be a type of problem that we've actually solved in other areas where, if you look at, reading ahead and things of this nature, we've had to sort of anticipate doing things. And again, the concept here is you may be able to do something similar to the keys. So once you have the keys in the cache, how they get used is every I/O, reads and writes, essentially come down with a namespace ID and a key tag, which is essentially where in the cache do I need to essentially go look. But it's not quite that clean, because you could actually have multiple namespaces, and you've carved up the key cache so that different namespaces have some part of that. So you could actually have key tag 1 for namespace 1 has to be mapped into a particular location in that overall key cache. Now the drive takes care of that for you because it looks at the namespace ID and the key tag. But on the drive side, the drive vendors have to basically deal with, I have this much space and it's allocated in this particular way and basically you use it.
So Eric,
yes.
You said the host has to carve up the key cache, but that's really purely handled by the host. There's no physical implementation part of the cache that sorts that out.
Yeah, so there's the cache can be on the drive. The host can say, I want 10 namespaces and I'm going to allocate of this key cache 100 for namespace 1, 200 for namespace 2, and you couldn't go on to it. Now, at some point, if you need to change that, it is possible to go in and make adjustments to that. So it's not cast in concrete, so to speak. How you go about doing that is can kind of be interesting. Yes.
So this is exactly what we do in software when we have today software-based encryption. Key manager will get the keys and cache them in memory in the on the appliance. But one feature that is very common is that because the keys are in the key manager, which is external, the keys, there's a possibility that they are compromised. And when the keys are compromised, we go and say we invalidate the key and we tell the software to re-encrypt the whole thing with the new setup. So how is that possible?
So to simplify the question, so if you've got a scenario where you've got a potential compromised key and you need to essentially cause the rekeying of the data, essentially the process that you would use is the same. The host would own the problem of I've got the old key and I've got the new key I want to use. Both of those would need to be in the key cache because I'm gonna read using key tag 5 and I'm gonna write with key tag 6. So the process would essentially be the same. The host completely controls.
The host is the orchestrator.
It is the orchestrator.
This is just doing the decrypt encrypt.
Yeah, think of it as you've got the encryption engine on the drive, so you're not paying the penalty of the encryption piece, at least where the data is actually on the media, but you have full control of the keys. And sort of elaborate a little bit, if you think of a situation where you might have multiple virtual machines talking with separate key management servers, so they're controlling their own ecosystems and passing down using Keeper IO. The host knows nothing about where those keys are all coming from. Those are all actually managed inside of the VM. So it gives you a different way of looking at a different angle, if you will, of dealing with this. So we see that VMs and containers, potentially cloud, you could actually abstract this even more if you think about cloud, where you could potentially have a cloud service customer passing in the keys that they want the cloud service provider to use, who in turn passes that all the way down to the media, because normally you don't have any control of what's happening, how the encryption is being done. Well, why is this important? You want to make data go away. You just don't provide the keys, and the cloud service provider doesn't have access to the any of the materials that you previously, unless there's some way that they cache the keys or something. Okay. Yes.
Can I add one more?
Please.
So, to your point about a compromised key scenario, the protocol defines a mechanism to clear a key, either serial key or RZ key.
Right.
So, once you have done that, once we read it over, write with a new, you can say, go clear this. I don't want you to remember that key anymore.
Yeah, we do that in software.
Yeah.
We have to tell the drive to clear it. clear the cache.
Yeah, so for the recording, the KeeperIO has the functionality of clearing a single key or clearing multiple keys. So back to the scenario where you're rewriting the data when you're all done, where key 5 is the compromised, you basically clear key 5 and it's gone from the drive. It knows nothing about it then.
Yeah, with the SCDs, the compromise doesn't arise because the key NVMe never leaves the drive. So, technically there is no compromise possible.
If you're comfortable with the key management of the drive, and not all customers are comfortable with that. So that's one of the things that comes up. Okay. Trying to get the. All right. So the whole point of this diagram is to sort of help draw attention to a couple of things. I mentioned the scenario where you've got multiple VMs or containers that are interacting with one or more key management server. This is when you start talking about things like secure multi-tenancy. Your security infrastructure may actually be separate for each of your tenants, and KeeperIO could be important because if you think about an Opal drive and you personalize it, the personalization is with the underlying server, the host. It's an authentication mechanism. None of the VMs know anything about that. It's, that relationship is set up. In this case, you actually could set up multiple namespaces, have the namespaces assigned to the various VMs, and using KeeperIO, you have the ability to control the keys for the underlying encryption on the storage system. So that's one aspect of it. Another one that we like to point out is that it isn't necessarily valid to assume that the host that's using the drive is managing, is in control of the management of the drive. So for example, you might actually, in a NVMe over Fabric kind of scenario, you might actually have multiple hosts that are accessing that drive, and you want to restrict what any one of those hosts can do. So the management can actually be handled independently of the usage. So you could set up getting the wrapping keys in place and say namespace 1 and 2, this host knows about namespace 3 and 4, this host knows about. They then can load their part of the cache. They don't have access to the full cache. They have access to the part of the cache for each of those namespaces that they have. KeeperIO gives that capability. But this is an important thing to keep in mind because you may want to manage these separately from the drives that are actually using them. And KeeperIO has the ability to basically do that using the NVMe interfaces. So this basically is trying to show that not only can you deal with multiple key management servers, separate key management servers, but you can also deal with the management piece a bit separately. And in the SSCs, we go into a lot more detail about what actually happens. So if you look at the diagram and the specification, you'll see that what's actually happening in the conversations here. Yeah, yes.
Is the text already defined?
So it can be. So there's initial KEK that needs to be established. There's a couple ways that it can get done. One is it's loaded, can be loaded with over a plain text KEK comes down in a secure environment that gets established. There's a PKI-based mechanism that can be used to get the KEK installed. The KEKs in general are retained. So if you do a power cycle, once you've got the KEKs loaded, then it makes it easy for the host or hosts to be able to reload the key caches.
How do you unlock the device? Is there a password for the KEK?
First of all, what is a KEK?
A KEK is a key encryption key. It's a wrapping key. Yeah. So, so there's not an authentication mechanism like Opal drives. Part of this dialogue that takes place is using the key encryption keys. So if they're loaded, then if a host is basically going to pass down keys, it actually has to know the correct key encryption key because the drive is going to be looking at that to essentially unwrap, and if you can't unwrap the keys, then think of it as a more of an indirect authentication. Would you say that's But if you don't have these key encryption keys, you could shoot stuff down to the drive, but the drive is like, I don't understand what you're saying.
So the host has to pass it.
So the KEK is being used to wrap, keys that are coming out. Now once the cache is loaded, then you don't really need to worry about the KEK because then you're just using namespace ID. But if you haven't successfully loaded the cache and you go to do I/O, that's an error condition that the driver I don't have any keys.
So it's still true that you cannot have Opal and SSC active, Opal and KPIO active at the same time. It's one or the other.
That's my understanding where we're at right now. Yeah.
Even though we've rolled it.
Yeah. Now the
drive can, the drive can support more than one SSC,
Correct, support, yes.
but active, I think it is one.
Only one, yeah. Okay, that's what I last remembered. Thank you.
Yeah, and I mean, so the question is, is it either or for Opal versus KPIO, and at least from activation, and that's the current situation. Now, if you're activating KPIO at the namespace level, and you've got namespaces that are established already, then you could use, so you could activate it and only use one namespace on the drive that's KPIO, but the other ones might be associated with Opal, but you don't have access to those. But activating KPIO on a namespace won't wipe out the data that's associated with what an Opal managed set of namespaces. You just can't get at the two of them at the same time because you only have access to the keys on one of those. Okay, so we've already been sort of talking a bit about some of the mechanics here. So there's a lot of sort of setup kinds of things that you need to sort of pay attention to. There's some discovery that happens on the NVMe side, which will basically let you determine whether or not KPIO is supported on the drive. So this is typically the first thing that you would check for us. Is this a drive that's supports it? You also want to find out essentially how big is the cache, and maybe how many namespaces that the drive will support. So those are, it seems like pretty simplistic, but you kind of have to know that to be able to sort of take to the next step. And then there's a discovery phase on the TCG side that you can then get additional details. And the combination of those will help you figure out what are your options in terms of getting the initial key encryption key down into the drive. And that's important because that's used to then get subsequent wrapping keys that are associated with each of the namespaces. So these discovery mechanisms will tell you basically what you can do, what your parameters, your limitations are. And a bit of an eye chart here, and this is basically showing the dialogue that you typically would go through. So the slides will be available later if you want to sort of see the specific mechanisms. This kind of shows you the back and forth that takes place. And again, you're setting up In this case, we're showing multiple namespaces and setting up the allocation of the space, because you need to tell the drive, how much of the key cache you will be using for each of the namespaces. And that becomes important because you're not allowed to exceed that. So if you say, I'm going to give you 1 key slot, then you may be pounding on that with injections an awful lot. So, it's important from a host perspective to figure out, what kind of balance you need. Now, if you're doing something where you're using a single key for, an ejectory mount point or directory, then this might not be, a huge issue. But if you're, doing it for every user or every file, then how you manage this becomes important. And as I said before, the key cache itself, so these are all the media encryption keys, they are volatile. So if you reset the drive, power the drive, those keys all go away each time. This is sort of talking to some of the admin side. So this is the management piece. And as I mentioned earlier, a key detail, pardon the pun, but the recognizing that you can manage the drive, this setup, separately from the drive that's using it is important consideration. And so you might be using NVMe MI, for example, to manage this initial sort of configuration aspect of it. So the loading of keys is done with an key injection mechanism, and this key injection mechanism is where we're using the KMIP specifications. So the idea is, so we're basically using KMIP commands and the structure and format from KMIP to do this. Now, you don't have to be KMIP literate, because KMIP is the key management interop protocol from Oasis, and it's used for key management servers communicating with key management servers and various clients working with key management servers. In this case, we're using a fairly small subset of KMIP for things like gets and sets and queries. It's a very, very small number, but it allows us to not have to go off and redefine, think of it as like a data stream definition. We use the way KMIP has specified this, and we just follow. And as I said earlier, potentially gives the ability to use KMIP from all the way from the key management server down. Think of the host is a client to both sides. So it's a client to the key management server, it's a client to the drive, and in theory could function as a proxy. This is iTest. So KMIP has binding in terms of for example, XML versus binary. This is a sort of the XML view of the KMIP commands that would essentially be injected in the drive. Now, we're not using ASCII text, if you will. The idea here is that you're actually using binary to inject this, so it's fairly efficient in terms of what's going on. The other thing, and again, this is where a little bit of KMIP knowledge is useful, is using a batch command. So you're able to group multiple transactions as one sort of batched up item, so you could be injecting multiple keys, MEX at the same time. And again, this is just further examples of what it would look like in terms of the command set to perform certain kinds of operations. So one of the important pieces of this interaction from an NVMe perspective that the host has to track is both the namespace ID and the key tag that's being used. And the key tag is pretty straightforward because the host is driving. It's saying, I want you to put the key in location 1 for the namespace 1 part of the key cache. But it is important, though, that the host actually does know what namespace ID is being used and that the drive has been made aware of that, because that combination is essentially used for the access of the cache. And this is showing an example of what the write would look like. So here you're seeing the namespace ID, the data, and the various pieces of information, and then where the key tag would actually show up. So this is getting down into sort of the nuts and bolts on the NVMe side. And then what happens on the drive side. So it picks that information up, essentially is doing a lookup to get the key, and then once it has that key is used by the encryption engine.
So the question, those are for reads and writes. Is the key tag present in like a copy command or right?
So a copy command, so the question is, this is for reads and writes, how about a copy command? A copy command is going to basically be a combination of a read and then a write. And so it's gonna manifest itself in this dialog as a read using a particular key tag on that namespace, and then a write. The question, of course, is are you doing the write with the same key, or or in the case of rekeying, are you using a different key? So you could do that. So copy isn't a single transaction from a KPIO perspective. It's a read and a write.
So were you showing the NVMe commands back there?
So in this example, yeah, there's a series of writes, yes, with a read at the bottom.
So the key tag, yes, with the copy command, you would need to restrict the copy command so that each range has one specific key specified.
Each range is special descriptor for this entire call. It's all in
It's in the description.
4055.
Yeah, it's TP 4055. Yeah, but for it to work with a KPIO enabled drive, it needs to know what key tag to use. So, as I said, copy is basically two functions. So as long as it has the key tags needed, it should be fine. And of course, they both have to be loaded. So if you attempt to copy and you got the one to do the read, but you don't have the one to do the write, then that's an error condition. Right.
But in general, every KPIO is not going to have a key. Every KPIO is not going to have a key. So even you're saying the copy command, we have to do multiple reads and writes, but it is a big copy range. Right? But if you have a key per file, the host is managed.
It needs to
Yeah.
be a deeper range in that.
Yeah. So the KPIO isn't thinking about LBA ranges. It's just thinking about I've got this amount of data coming down. So whatever that smallest piece of data that can come down to the drive is, you have the ability to change the key for every one of those if you wanted to. You just have to make sure you've got them loaded before you use them, either on the writes or on the reads. And that's one of the things as a drive manufacturer. It's like, so how big does that key cache need to be? That's part of, one of the sort of and because of the nature of that cache, it needs to be relatively fast. It's volatile, so that's one of the interesting issues is, well, if you were going to do this, how much, if you're using Hibbard, how much would you want to have how big should that cache be? And part of it's driven by, well, how many namespaces are you going to support? Because if it's a single namespace, kind of looks like a self-encrypting drive. If you broke it up into 1024, still looks like self-encrypting drive, but that's a small number of keys. It's these environments where you've got a bunch of VMs that are doing something exotic, where it starts getting kind of interesting.
You mentioned the read needs to provide the tag also, so there's no identification on the drive of which key was used to encrypt the block.
So that's a very good question. So the question is whether the drive has any knowledge, on a read, whether the drive has any knowledge of what key was used. There's an optional feature that for wrong key detection. And so the implication there, because this gets into an implementation detail, and remember, it is optional. It's one of the things you can check to see if it's supported. The implication is that the drive may have retained some sort of information about what keys I may have seen when this data was being written, so that when I get a key, I can actually, oh no, that's not the right key. I don't know what the right key is, I just know that one's not the right key. So there's different ways that you could do that. We've had conversations, in the work group as to, is this viable? And the answer was it's viable enough that we include it as an option, but it's not a mandatory feature.
The block itself is not self-described.
So how you go about doing this is interesting. I'll give you an example of something that was discussed. It's like, so in theory, the drive might have to know something about every key it's ever seen from a keeper IO perspective, even if you are using it in a new environment. It's like so any data that's basically resident, you would have to have some way of being able to do it. So it's not a trivial feature to implement. And again, it's back to part of sessions like this is helping you understand how you could exploit this. We are looking for what would be the killer app for this. And some of that would actually drive, what's the importance of wrong key detection, how big the key cache should be, how many namespaces, kinds of scenarios. I shared some of my thoughts, from cloud and virtual environments, but the other side of it is, depending on what happens with NVMe over fabrics, that could add to some interesting dynamics on this as well, because that could easily expand the number of hosts that are essentially accessing drive. Okay. Yes, go ahead.
So we could have ranges, I write a big range, but I read different overlap or different ranges. You could have different encryption keys, and I'm trying to read. And then detection, being able to detect that, hey, partial read is correct encryption key, and the partial read is the wrong encryption key. Again, that's also part of the ability, optional.
Yeah.
How are you doing on time? Because if you're short for time, I will not ask.
We've got about 8 minutes. I mean, part of this is to make sure that your questions are sort of answered. Yeah.
Okay, so to the point about what Eric mentioned, the optional facility to abort the command if it's not decrypting properly. If you could just arbitrarily, take something, encrypt something onto a drive, and then pull it back out with the wrong then that becomes a device that can be used to arbitrarily encrypt and decrypt information. And that, at least in the US, makes it subject to some other arms control or whatever.
Yeah, export control, yeah,
Yeah, export controls.
yeah.
Just get garbage out if they use it.
That's right, but nevertheless, you can then take that data, send it to somebody, nobody in the center can understand what it is, and a lot of countries get upset about that.
Yeah. So this is, yeah. So this is one of those scenarios where being able to generate an error, helps you avoid some of these kinds of problems. And,
If you dip it in the butt, then there's no question.
yeah, and again, we're definitely early days with this technology. So, the vendor community is trying to understand what the potential need is, how they should, what sort of functionality they should have. On the host side, it's, how could we exploit this? And I don't know that we've had I wouldn't say we've necessarily come to any sort of alignment, but this is, again, part of the conversation here is, well, if you were going to do something like this, what might you need? How important would this feature might be? And
You said that it's address ranges that it's encrypted, and that you're going to write the address ranges. Is that address range, what's the granularity of that address range?
I mean, for like a block?
Oh, really? Okay, so if I have, let's say, a big write menu, and it crosses 5 address ranges, how do I send it such that I
Every
break into 5
every write that you do, whatever the limit is on a write, has to have a key tag.
Okay.
So
I'm thinking of atomic operations, so if I have a big file write or a big thing write.
however that would get written using NVMe, so the write that would be issued, so most likely it's being broken up into multiple writes. Each one of those would just need to have the right key tag on it.
Gotcha. You have multiple keys per file,
That gets,
that's troublesome. Yeah.
So you could be using the same key tag to write, your write is encrypted by NVMe.
Yeah.
So you can, if you have more data to be written, you can use the same key tag for multiple chunks of data.
Yeah, that's it. We do this in our software. The way we rotate keys is based on two things. Whether how much amount of data you have written so far from T1 to T2, or how long has it been since I rotated the key.
Gotcha.
So we don't rotate the key for every file. We rotate the key based on the amount of data or the duration from the last rotation.
Now, like you separate the read key from the write key, that you actually can have somebody with read access to allow, but not write access, and its key is forced. What about PIN?
No, that's not the case.
Well, it's not the case.
yeah. So from a keeper IO perspective, I mean, yes, you've got to have a key tag for each read and write, but it's not restricting. I mean, they could both be using key tag 5, one for the write, one for the read. So it hasn't changed the dynamic on the host side. Unless, of course, the host basically said, I'm going to do write, and then it deletes the key tag, and then you go do a read, and it's like, oh, there's no key tag. There's no key in that slot that you can use. And you can do things like you can lock down the cache. So if you've got a scenario where I want certain keys because I'm going to use them all the time, and I know I'm going to use all the time, you can lock them into the cache so that you don't accidentally you get too efficient and suddenly you lose a key that you now got to go basically inject into it. So it does have some smarts that let you do this. You can selectively control which keys are basically removed. You can lock keys down. And even the lockdown function could actually be part of the management interface. So you could force, I'm going to load these keys and lock, that you can't load anymore. These are the only ones you have access to. So
one other feature that we have is that as soon as you detect that the key is compromised, we can flag the key as a compromised key so that no more writes, no more new encryption can happen with the key. But we need time to rekey that thing. So for duration, we can use this to read, but no more writes. And then we have a key destroyer, which is similar to removing it from the key.
Yeah. So again, all that logic would basically be on the host side.
So it will still
Yeah,
be on both sides,
yeah.
and we have to manage it.
Yeah, yeah. But it gives you the ability, I mean, you're already managing that, so this just gives you a mechanism where you could expand that management down into sort of the drive level. Yeah. And I believe we're just about out of time. I'm going to just do a quick scan. So yeah, it is possible also to disable Keeper IO, so you could be all done, and you wanna basically, okay, I'm gonna stop using it. Well, why would you do that? Well, if the drive speaks both Opal and Keeper IO, okay, I'm done using Keeper IO for now. You know, reset the drive and bring it up in Opal mode, and do whatever you're going to do. And you also have the ability to essentially do a revert kind of function, so you can say, I want to get rid of all this stuff, and again, you have the ability to do that. I believe that's. So in the last minute here or so, this is another way of thinking about encryption at the drive level. It helps deal with the problem of maybe I don't really trust the key management in the drive, so okay, you can take ownership of that. That's what this does for you. Looks like a very interesting option if you're dealing with virtual environments and maybe cloud, and you really don't have any limits on the number of keys. It's whatever you can manage, go for it, kind of situation. So hopefully this was helpful, give you a little more, it's more of a, rather than reading the spec to you, but give you a little more idea how we envision that you'll be able to take advantage of it. And we're very interested in potential use cases and whatnot in the future.
One last question.
Yeah.
If I were to offload encryption to QAT device, is the encryption at the disk level, is that much faster than offloading? It's very similar to what it is. In effect, if I were to offload it to a special
That's an
CPU.
implementation question.
Yeah.
There is no fast to that, right? You've done the encryption somewhere else, and you can just write the data.
Yeah. Yeah. So this is more of if you were using something external for the encryption. If you're doing,
Today, the main problem with the data encryption at rest is the CPU that we burn. Use the encryption device. That's the biggest CPU consumer for us.
yeah. So if you can offload that to a drive, but you want to manage the keys, this may be a solution for you. And their Keeper IO is, I've looked at it for some other interesting applications. So you may see the ability to use this in other ways down the road. But this is the initial, thinking about it from an SSD perspective. But Keeper IO might be an interesting tool that could be used a little more generically. You've got an encryption engine, keep the key management simplified, whatever that might be. This if it's in the NVMe ecosystem, it might be usable. Sorry.
There's nothing in the spec that allows the device to communicate the mechanisms and supports for injecting keys.
So there's a discovery mechanism at the NVMe level, and then there's a discovery mechanism on the Keeper IO side.
Okay.
So
So the device is capable of saying, okay, I support the
send and
receive
yes.
mechanism.
Yeah.
And these are strictly defined in the spec. So say, okay, so I'm a communicator, and say I want to support this for virtual functions being passed to.
Right.
And I wanted to do some kind of another protocol where I could just inject keys for a tenant directly into that drive before I load it up on the virtual machine, without using KPIO. Super simple where the tenant provides a key and just says, please use this for
So yes.
the operating system, the guest doesn't have to know about
Right.
any of this. It just goes on.
So in theory, you could actually do that. I mean, this is all running down at the NVMe level. So you could at a very low level, check the drive. Does it support KPIO? Yes. Oh, well, then on behalf of, I'm going to be able to support 50 VMs, and I want to make sure that each one of those VMs is managed separately. So at the hypervisor level, you could literally say, okay, so I'm going to set up KPIO. I'm gonna deal with, you know, these 50 VMs in a particular way, load the key cache, and then whatever each one of those VM does, you just automatically you take their reads and writes and assign it to the key. In that case, it's under the covers. The hypervisor or the operating system is basically managing the KPIO pace. And yeah, there's some folks that are kind of looking at that where KPIO is being used, but it's completely transparent to, you know, everything above it. But again, you don't necessarily have to do that. You could potentially, in a cloud environment, expose this all the way out to your cloud service customers and let them provide the keys, which would go all the way to the drive. So lots of flexibility here.
I think that might be difficult if they had to wrap the keys in the
This is back to, you know, having some of the KMIP functionality is, in theory, you know, you may be able to do some of this. But you're right, getting the key encryption key handled correctly all the way down from the end user would be something you'd have to look at very carefully. But it theoretically it's possible. All right, well, thank you very much for your time, and we look forward for your interest and you know, if you have any comments or thoughts on it.